analyst since roughly the time in which we pretended that video was made. And this is the company I'm with now, Method, our corporation. You may know me from the Optimizing Oracle Performance book. It's been mentioned a time or two. People ask me, am I writing a new book? And I say, well, there's this thing, which is a one-day course, and it's a book. So it's officially a book. It's just not published by O'Reilly or any press or any of those guys. It's kind of self-published. So back to the regular show. I think we're about 10 slides down, so we're on schedule at this point. So here we go. Millsap's grand unified theory of tuning. Well, first thing I want to point out is you probably have noticed I did this, and you might want to know, so what's with the quotes? And by the quotes, I mean these quotes. And we'll get to that shortly. There's got to be some building of suspense, or you won't want to stay. So this is the suspenseful thing that you're going to have to wait and see. So part one, I want to talk about the what I'm calling the grand unified theory propositions. So here we go. Next slide. My proposition is that there are two types of performance problems in this world. There are response time problems, and two, there are inefficiencies that aren't response time problems. So therefore, my grand unified theory proposition number one is this. You must be able to attack response time problems for the specific tasks that the business cares about. So for example, imagine that posting hurts and you're required to fix it. You know, the month-end post where you close the books and all that. So why should you care? Well, this one's easy because people with torches and pitchforks will follow you home. Proposition number one. Good proposition number two is that you need to be able to attack inefficiencies that aren't yet noticeable as user response time problems. And an example of that is that posting takes 3 hours. It should take 2, but nobody really cares. So you might ask, well, then why should you care? And the answer is simple, because you waste money when you waste cycles in your system. Whether anybody really cares or not, you're actually wasting money. So the way that works out is that waste causes this extra hardware that you have to buy, and the extra hardware you have to buy means you have to buy extra labor to run it, and the extra labor and all that means you have to have bigger software licenses, and that all adds up to a higher total cost of ownership. And yeah, this one's got the better color on it, so you can see the arrow going down. And waste makes other work go slower, and this picture cracks me up, even your fast stuff. Now, I'm sure these 4 guys were thrilled to find that there was a Ferrari-only lane on this highway, but still, they're stuck behind each other. So to recap, the two GUT propositions are you must be able to attack response time problems and efficiency problems. This concludes part one. We will move now into part two, the historical perspective. So I showed you the graph. I've been around a really, really long time, and now that I've lived this many years, I tweeted a while back that actually my biggest fear now is behind me. I can no longer die young. So I have lots of road behind me, and I'll explain some of the road behind me. So let's start at the beginning. In the beginning, and for me that was 1989. It was Oracle 6026, and this is what tuning was. Tuning was bstat, and then a few minutes later, or half an hour later, or an hour later, you run estat, and you get this file called report.txt. And then there are all these other things that you'd look at too. There's tons of them. There's operating system stuff, there's $V stuff, there's X stuff if you're courageous and good. But there was a lot of stuff there. And the algorithm for using all this stuff was as follows. You look for bad numbers. Bad numbers. And bad numbers are supposed to represent inefficiencies. So the problem is, well, how can you know whether these numbers that you see that look bad are what are causing a specific task to be slow? Because what you get is this mountain of data, this mountain of paperwork. And I've seen people literally slide this hunk of paper across the desk to us and say, show us what's wrong. And you know, people in the room are all shouting out different answers about what might be wrong. So my problem was always that I didn't understand when somebody that was senior to me and more experienced than I would look at one of these big bricks of paper and go, oh, here's what your problem is. My problem was, well, how can you possibly know that that one hypothesis is the only correct hypothesis? There may be alternative hypotheses that are right as well. And it reminded me of when I was a little kid and you take the astronomy class, and somebody takes you out and shows you the night sky, and they point it up at Orion, and they go, you see it, right? And you're like, I see what? And they go, no, you see it. Look real closely, and what you'll see is this guy holding a lion's mane, in the tail, and the belt, and the sword, and the club. And I never really got that. I mean, I could see when they showed me the picture that, yeah, sure, those stars look like a belt when you draw it that way. But who says that's what you have to see, right? So you look at these stars, you look at the stack of reports, and maybe you see something totally different. Why not, right? I mean, you can't. It might be Mickey's nose just as much as it might be a guy's belt. So the problem with B-stat and E-stat, and this problem sort of lived through the ages with what a good friend of mine used to call Uttlebistat and Uttlestat, and all the way into StatsPack, and in fact all the way even into to Ash and WR, is you get this big bunch of stuff, and you've got all these theories, and some people see this and other people see that, and it's very difficult to know, and sometimes you even can't know from the data that are in that big stack of paper what the problem is. And here's an example of that. Imagine I showed you some data and asked you, what is your task problem? And the data look like this. The total system looks like it's just utterly dominated by latches, right? 74% of the, quote, wait time. I really should have worked these out last night. I'm getting cramps from doing this so much. But latches are completely dominating the wait ecosystem of your application. And you have to be an idiot not to derive the conclusion that, well, the problem for posting or whatever is this latches thing, but it actually may not be true. And this is the kind of problem that people try to solve their problems. They call us, and we end up going and seeing these weird cases that apparently aren't that weird because they've sustained a lot of payroll for the last 15 or so years. But this is what can also happen. And look at this. If your task has a completely different character than the average task on the system. By the way, there may not be an average task on the system. There's, of course, an average across tasks, but there may not be any task that looks like the thing on the left. By itself, this is really your problem. In this particular case, you've got an I/O problem, and yeah, that works. So does the green thing, I suspect. And this is just absolutely not your problem. And here's how it happens. What's really happening is that there's other stuff running on your system besides the stuff that you're interested in, and the thing that you're interested in has a particular profile that may not resemble in the least what other things on your system are doing. But if your urgent thing that has to get fixed by this Friday, or you're going to get hanged by the neck until dead, or your business is going to go out of business, then you need to see these numbers, not these numbers, which are highly influenced by those other tasks numbers. So the point is sometimes you cannot know. It's not that you're dumb, you just don't see it, or you just have some sort of deficiency that prevents your brain from being able to make the right decision. Sometimes you do not have the data that will allow you, unless you're really lucky and in fact not very well trained, because you'd have to go really far off the rails to guess what the problem was if you only saw the first couple of columns on the prior page. Sometimes you can't know until you look at it. And when I say it, I mean the right it, which is the thing that the business needs to go faster today. So just kind of as a recap, this is what the total system might look like. Your task might look something totally different. When you don't know this, you end up with that. So one day, it turns out in 1991, I had an epiphany. And it wasn't I had an epiphany. An epiphany was given to me by a peer inside Oracle. I hesitate to say peer, a colleague, a mentor-type colleague. So in 1991, and it really doesn't matter what Oracle release it was. I know what Oracle release it was, but it could have been anything. It could have been 12. It could have been 5. It would have still been the same lesson. But back in those days, the golden rule of tuning was this, and trust me, that's really gold on my laptop. This buffer cache hit ratio thing needs to be 100%, and that's the definition of greatness. If you've got a system where your buffer cache hit ratio is close to 100%, then spot on, you're good to go. The buffer cache hit ratio is defined as the ratio between the number of logical IOs LIO minus PIO is logical IO count minus physical IO count. So how many times did I go attempt to find a buffer in the buffer cache and not find it, divided by, and find it, divided by the total number of times I attempted. So if this ratio ends up near 100, then what that means, 100%, that means that your likelihood of when you've gone to the cache has been extremely high, that you find it in the cache without having to go further and read stuff off the slow spinning Rust devices. So this is the epiphany that was given to me. A gentleman named Willis Raney, not Rainey. However, he did one time leak the word instantaneous, at which point I said, aha, it is Rainey. Anyway, Willis Raney taught me that a higher database buffer cache hit ratio is not only insufficient as the basis for measuring whether your system's good or not, he actually taught me that a high buffer cache hit ratio is a bad thing. And if you see a high buffer cache hit ratio, here's how you go fix the system to make it faster. And the demonstration, of course, the reaction most people have is, what? So the demonstration that he gave me was to imagine two queries that are written differently, but they return an identical result set in all cases. So query Q1 and query Q2 always give you the same, presumably correct answer. And he asked me the question on a whiteboard, which one of these do you like better? Q1 has a 99% buffer cache hit ratio, and Q2 has a 90% buffer cache hit ratio. And he said, which one of those do you like better? And of course, you want to say I like the top one better, because that's what I've been taught for my whole Oracle career up to this point. But we're at the whiteboard for a reason, so apparently I'm just going to keep my mouth shut and we'll learn something in a moment. And what he went on to show was the two additional columns that you need to see before you can calculate why the buffer cache hit ratio is what it is, and these are the columns he showed me. What if query 1 requires 100 touches on the database buffer cache and 1 physical I/O, but query 2 requires 10 touches of the database buffer cache and 1 physical I/O? Which one do you like better? Well, I like the cheap one. I like the one that does less work to provide the same exact identical business benefit. So I like this one, I don't like that one, and therefore I like the 90% better than I like the 99%. And his point as he continued, Connor McDonald gave the best demonstration of this I think I've ever seen by writing a program that will make your buffer cache hit ratio whatever you want it to be. An input parameter is how many 9s do you want, and then he will run crap SQL that will make your buffer cache hit ratio achieve that many 9s of perfection if you want to, but it won't speed up your system. So the point there is you can't count on the ratios to guide your analysis process, and therefore this big stack of paper, that you're trying to figure out what is it that I'm supposed to do with it, it's just, lots of people shouting different ideas. And the problem is that the rules that were in a lot of people's heads were just wrong. So which leads to this, and to a house and some cars and a lovely family and 15 years of payroll after Oracle. So another man who knew this is a gentleman who's a friend of mine named Dave Enzer, and this is a funny picture. I won't tell you why it's a funny picture. I'll let you figure that out for yourself. What do you think? You know who all 4 of these people are? Well, 3.5 of these faces. Well, that's Connor right there. That's Connor McDonald. That's David Enzer in the middle, and that's Tom Kite when he was about 9 years old. And anyway, Dave Enzer wrote the book called Oracle Design. It was one of the best Oracle books ever written at the time when he released it. And what Dave taught me was this. To tune, you watch the user, not the DBA. Now, up to that point, I'd always been taught to watch the DBA like hell, because the DBA is where all the performance stuff is. But Dave taught me, and he taught a lot of other people inside Oracle, to fix performance of a system, you look at the user, because the user is basically where performance gets defined. And that was very strange thought to a lot of people, and that led to the question, well, how does one do that? And in the early days, the primary tool for doing that was this thing called TK-Prof. It was an Oracle developer tool that was introduced in Oracle version 6 with the very first trace data that came out with the Oracle version 6 of the database. And this is the kind of stuff that TK-Prof showed, and I've still got books from back in 1991, 92, where I've got slides that show information like this, and they've got little things circled, and they've got another thing circled, and there'll be a line that says this big, that small is bad, here's why, and it was good training. And it's what you need if your problem is SQL, and of course, here we go again, your problem is always SQL, Superman says. So that kind of takes us up to about the early, I guess, maybe early 1990s. Well, in 1995, and this is the domain of roughly Oracle 7, I happened across a young man who worked for me at the time at Oracle when I ran this thing called the System Performance Group. And this gentleman's name is Virag Saxena. And Virag is the very first human I'd ever met who was able to go on site. And by the first morning he was there, he'd show up at a customer site 9 o'clock Monday morning, and about 11 or 12 o'clock Monday morning, I'd get a phone call, and he's the first human that I ever met who was able to say stuff like this. I can reduce response time by this many seconds if you let me do this thing, that thing, or this other thing. Virag used to call me and tell me that. And then I would help him get permission to do Y, and I'll be darned, X would happen. First human I ever met who could do that. So my goal, of course, managing a group like this is to put that kind of thing in a bottle. Which brings me back to those quotes that I talked about a while ago, these quotes that were on the title page. The problem is that really tuning isn't good enough. And if you look up tuning and you look up tuning books, tuning is all about making these sort of almost random incremental improvements, sort of just looking everywhere for ways that you might incrementally improve something, whether it's a car or an airplane engine or a boat or an Oracle database. And tuning really is defined as making some component go faster. And you feel like you've succeeded if you find a component, you can make it go faster than you have tuned. But what we really want is we want to maximize the economic value of a system. We don't want to, for example, I mean, imagine it may be inconceivable in your mind that this could exist, but they do. Imagine that you visit a perfectly optimized system, a perfectly tuned system, and somebody asks you, what are you going to do? Well, are you going to look for stuff to do for 6 or 8 months before you decide, well, I've tried as hard as I couldn't make it go any faster, I must be done? Well, it's a really inefficient algorithm for deciding whether you're finished or not. Tuning tends to be more trial and error, and what we want is more informed action. We want to know in advance what's going to happen when we try something. And I've been in a lot of places where people can't tell what's going to happen if we try something, so what do? Well, we can test it in an expensive system, which you should do, and then move it to production if it works, but it's a lot better if you kind of know in advance what's going to happen so you can choose among the best of the 13 alternatives that you might actually go out and try to implement. Tuning really is weak accountability. Well, I was there and I tried my best. Oh, okay, that's fine. Well, we really don't want that. What we want is accountability to a forecast. We want somebody who can, by noon on Monday, say, this system has this much potential, and I can get it for this much price. This many hours of work, this many people have to go off of making new features to fix the old ones, but if you do this, I can give you that. That's what we want, accountability to a forecast. And finally, tuning is kind of a success measured by effort sort of a thing. There's a poster, one of these inspirational posters that people put up on the wall that, like the teamwork one where all the guys are parachuting out of a plane, they're holding on to each other's hands and they make a star, and it talks about how important it is that you not think about yourself, when you're part of a team and all that. There's one that I particularly find just disgusting. It's a picture that's in landscape mode, and it's a picture of some hands dunking a basketball, throwing a basketball violently through a rim, and the net's all contorted. The guy's just going in hard. And at the bottom it says, success is measured by effort. Now I get that, and I get why I want to teach my kids that effort is a very important thing. But at the end of the day, no, success is not measured by effort. Who's more successful? Michael Jordan or a guy who tried twice as hard as Michael Jordan and didn't make it, didn't even get to the NBA? Well, there's value in trying hard. I'm not trying to denigrate that. But if you really want to measure success, from a team level or from a kind of a meta level, success is actually better if I can get just a horrifyingly large result for very, very little effort. That's efficiency by definition, right? So I think that success should be measured by results, and that's what we want. So what do you call that? We've got the thing on the left, and we call it tuning. I like to call the thing on the right optimization. So what we want, I will propose to you, is we want the thing on the right, and we don't want the thing on the left. And that's why I do the air quote thing around the word tuning. It's a word I kind of make fun of, because it sort of, to me, it conjures up that image of sort of low discipline operation. So on to part 3. How do we do all this? So remember, the goal was that we want this optimization thing that I described in the matrix by the really desirable characteristics I listed on the right-hand column of this 2-column matrix. And now we fast forward to the year 2000, right around the time of Oracle 8i, which my friend Mogens Norgaard has aptly pointed out that 8i is really 8.1. They just moved the dot from here up to the top of the 1. So what we wanted was some kind of a repeatable, teachable method. And a method is a deterministic sequence of steps, meaning I don't care who executes this or in what continent or in what time zone or what phase of emotional well-being. When they execute this method, they will get the same exact result as another person in a separate continent, in a separate time zone, in a separate state of emotional well-being. They will get the same result because it's deterministic and it's a prescribed sequence of steps. So I don't mean to say that there weren't methods at the time. There were, in fact, and probably the most popular and frankly the most useful one was this thing called the Oracle Performance Improvement Method. And it consisted of it looks like 8 steps. I thought there were 10, but we'll see in a moment if there really were. One of them, this is why I thought there were 10. One of them was number 4. It says review the top 10 list. And if you go look at the top 10 list, you see 10 ways that people commonly mess up their applications. And of course, every one of these things is just horrible and stupid, and you don't want to have a system that does any of these things. But there are 2 big problems with that method. One was, what if your problem is number 9? Do you really want to spend the time it takes to go through 1 through 8? Let me show you what 1 through 8 were. 1 through 8, well, here. 1 through 8 were, is all your SQL good? Are all your initialization parameters good? Did you get your I/O set up right? I mean, some of these are, that's like a week-long project, number 5. It can be, right? I've been to sites where they had, their triple mirror architecture, and they had all 3 of their mirror copies on their disks hooked to the same exact controller. So every triple mirror write is stacking up one copy behind the others, and that's a configuration error that of course step number 5 would reveal if you do that. But I mean, there's all these things, and by the way, number 4, you don't even get to this unless you've cleared the first checks up here. So the first problem is, what if your problem is number 9? I mean, you go through all these things that check okay, and then, ooh, finally we found it, and it may be 2-3 weeks, 2-3 months, depending on the complexity of the application. Remember I said there are 2 big problems with this method. What if your problem's number 9 is one of them. The other one is, what if your problem's number 11? There were only 10 things on the list. So what we have here is basically, it's like a full table scan. This method is a full table scan. This method says, here's all the things that you need to go do, and there's no index that tells you which one to go do first. You just kind of start at the top and do them all. It's like a full table scan of a table that's missing some rows, in fact. I mean, that's why a lot of people come to Oracle Open World every year. They get a notebook in their kit, and then they'll go sit at a presentation on a Wednesday morning at 9:45, and they'll hear something that they've never heard before. Oh, this TCP.no-delay thing. Oh my God, I bet that's my problem. I can't wait to go home and check that. I never heard of this before, and I bet you that's it. You know what, I'm going to call home and ask them tonight if they've got this problem. Well, there's 6,000 more just like that you might have a problem with, and it may not be that you're lucky enough to see somebody present about it on stage. So that's the problem. It's a full table scan of a table that's missing some rows, and what we really need is an index into the problem you're having right now, where the key of the index is the name of your business task. I know I got problems, but posting right now is going to get me hanged. I guess if it get me hung, I probably would want. No, I'll go off. Okay. So anyway, that all results in a lot of experience, a lot of different explosions. These are some of the thermonuclear explosions that we've seen in the 10 years and 1 week that I was at Oracle Corporation. And some of the people I've met, Virag is here, Anyo Kolk is here. He's the Kolk in the Kolk and Yamaguchi Yap paper. And then people like Dave Enter and these other guys too, and reading books like Eli Goldrat's The Goal, and reading books like John Bentley's More Programming Pearls, which talks about profiling software. This stuff all adds up, and I can't leave out this guy here, Jeff Holt, who apparently is having a baby in this picture. Anyway, results, we kind of distilled everything that we could from all these experiences and all these works of other authors into this Optimizing Oracle Performance book, which prescribed a method called Method R, and the R stands for response time, and it consisted of 4 simple steps. Number 1 is realize that your business is the only thing that counts here. The people that bought the machine are more important than the machine itself. And the people have certain desires in return for the investment that they have invested into this machine. And those desires trump anything the system might tell you about itself. So step 1 says target the right task. I've started using the word experience in place of the word task lately, because experience connects with actual people doing things, clicking a button, clicking a row, running a report. Those are all experiences, and that's what I mean when I say task. So task might be posting, it might be this button click, this row click, etc. Step number 2 is collect the details of why that code spent the response time that it did. And I mean a call by call, blow by blow. Here's what my code path did. It's basically the source code of the code path unrolled so that you can see sequentially every single database call or OS call that it made. And then step 3 is figure out what could be different. If I can improve this world, what improvement would I make? What call would I make less often? What call that I have to make can I make take less latency, take less long. And then you repeat until optimized. And optimized is defined as we reach our goal state. We run with as much spare capacity as we need to grow the business until the next time we want to have you come back and repeat this process. So, next slide. This is the kind of thing I'm talking about. If this is a representation of why your task took the time your task took, then this is the thing that you need to see. And the best way that I've ever seen to do that goes all the way back to David Enzor, where he taught us to use extended SQL trace data. By the way, the problem is not always your SQL. I need to go when I wink. So, meanwhile, back at Oracle Corporation, they kind of had a different idea. Now, you have to envision, if you're looking over here, you have to envision this timeline. And it started with bstat, estat, and continued through UDL, bstat, and UDL, estat, and then statspack and ash and AWR. And basically what this timeline represents is that every release of the database and every release of even, 0.2 and that kind of release have given us better and easier access to system workload statistics. For example, ash is a brilliant idea, and this is kind of the picture that I have in my head of what ash does. We've got all these different connections on an Oracle system, and possibly each of these connections represents a distinct human, but it might not because of connection pooling or whatever. But what ash does is every second, and these vertical grid lines are 1 second apart, is that every second ash will sample across the whole entire system what every session on that system is doing right now. And in certain instances, it will record and persist that information that it gains. So each red dot represents Oracle's having persisted the information about what this session is doing right now. And notice I didn't say waiting for, I hate that term, but doing right now. So the blanks are what Oracle refers to as idle events. So if you're doing SQLnet message to and from client, SQLnet message to and from DB link, virtual circuit status, there's 15 or 20 of these things that Oracle designates as idle events, and Ash just won't bother storing that data, and it causes the data that it does store to be considerably smaller, and you can store more data about more time. Well, next slide. One of the problems that I have is that nowhere in the Ash perspective is there really any delineation of where the experiences begin and end. So in other words, the little red box that I've drawn around this, you can't see that in this prior slide. I don't know if this is an experience and that's a separate experience, and this is an experience here and that's a separate experience. So there's nothing in the database that really records when these experiences begin and end. So there's no way that I can directly map. Now I can get kind of an approximate mapping if I just go, well, this session is that thing. But sometimes a session is more than, serving more than one experience. So the task perspective looks like this, and Ash really can't know what that, where those little rectangular boxes are. So anyway, we end up with stuff like this where it looks like this is what we need to do, and we might not ever see this second column group here. So we might not ever see the green column group. So here's how I think it all fits. This is the grand unified theory of trace data and Ash data. And if you go back to the proposition that I made at the very beginning where I said you must be able to attack response time problems for the specific tasks that the business cares about, I believe that the first level of attack needs to be executed with Oracle trace data. Because trace data allows you to answer the question, where does this task's time go? And it allows a developer to see how his code path or her code path stimulates the database to do various things, how it stimulates the network, how it stimulates every single thing between the app and the operating system that the database is sitting on top of. Now, Ash is awesome in that it answers questions about workload context. So for example, what happens if I trace a program and I find out, oh, I waited 6 seconds for NQ of a particular type that leads me to believe that I need a lock on a row that some other process is holding? Well, the trace data doesn't show you that. What happens if I find out that, oh, my process has been preempted and it was wanting to get CPU, but it couldn't, and I can see that in the trace data? What process was using CPU at the time when my process was trying to use CPU? The trace data doesn't contain that. So Ash answers questions like, for example, who had my lock, who had my latch, who was eating my CPU, who's fighting me for disk. Ash is awesome at showing you these kinds of things. So kind of first line of attack, trace data, second line of attack, Ash, for problems that are related to specific experiences that people can point up to you. So the second proposition of GUT was you need to be able to attack inefficiencies that aren't yet noticeable as user response time problems. And for this, Ash is awesome, because Ash is able to tell you who's using the most stuff. You can walk into an Ash repository and find out who used the most CPU yesterday. You can tell the login ID, you can tell the service module in action if you're blessed with an application that records these attributes along with the execution of different sessions. And then trace data can answer questions about task efficiency. If you find something that used way more CPU than you thought, well, you can trace it and you can find out, what does this thing do? I know you can find some of these things in Ash as well, but you can find everything in the trace data about every single sequential step that the developer inspired inside the database and the operating system that's sitting underneath. So the question, can this task be performed more efficiently, is something that is almost impossible to do, to prove without trace data. So one of the things that people object to about trace data is they say, well, it's just too expensive to turn on. Well, you don't have to trace everything. And in fact, you can sample with traces too. Ash doesn't record everything either. Remember, I showed there's several intersections of lines where there's no red dot. So with trace data, though, I can sample experiences. I don't have to trace this experience and every experience on these number lines. I can trace maybe just that experience. I can trace maybe 1 out of every 1,000 book orders. Maybe I can trace every posting that happens this week, because posting's slow and it'd be nice to be able to do that. Well, Oracle gives you the mechanism to do all these things. You have total control over it, especially if you're writing your own applications. So summary slide coming up. Here's how I see the tools fitting together. If you have a response time problem, I think trace data is the right first line of attack. And then Ash data provides the contextual information that you need sometimes to see who the competitors were that were causing your program to run slowly. If you're trying to fish down an efficiency issue, you're just trying to figure out, hey, I'm doing a capacity plan or I'm doing an audit of a system, and I want to know, is this system running efficiently? Well, sure, go look for top 10 bad things, look for the timed events that look out of place. You don't want log file sync to consist of 75% of your OS call duration on your system. And then trace data gives you the ability, once you narrow in on, this task looks like it's doing something pretty inefficient, then you can see, well, here's where the commits occur. A commit occurs behind that SQL statement, behind that SQL statement. There's 4 commits that occur behind that SQL statement. That's weird. You can see that kind of stuff in the trace data because it's not aggregated. It's not pre-aggregated into a form that may not be useful for the type of problem that you're experiencing. My mentors have taught me, try to be awesome. If you can't be awesome, at least be early. That's it. That's roughly 170 slides. I've got 2 more. One is if you're interested in how you do the instrumentation so that you can pick out the tasks, the experiences, that's what we'll talk about Thursday at 2:15. So do me a favor, run out, change your flights, and watch this presentation. And finally, I promised I'd put my contact information up on the board in case you need it. So with that, I'm delighted if you want to ask questions for another 9 or 10 minutes, and that'll put us back on schedule. So the floor is open. Eric Granchet. Oh, yeah. The question is when Virag would call me and say, if you let me do, I'll give you X seconds of performance improvement if you let me do Y. He was doing the trace thing. Yeah, he was looking at the trace data and he was deciding, you know what, this thing is making too many network I/O calls. The array fetch size is a ridiculously small number. If you let me make it 10, I can take these 13.5 seconds off this 14-second execution time. And he was just methodically going through the experiences, measuring them from the user's perspective, and attacking them one at a time. Had enough? Yes, sir. I can. Let's do that offline, unless a whole bunch of people want to hear about it. Is it code that you bought, or is it code that you're writing? Okay, I can help you more that way. Let's talk offline, and I'll give you all I can.
Quick announcement.
Yeah, bring it in.
We still have questions. If you want, next door they're doing ZFS Day, so these are a lot of the these are the kernel developers that came from Sun and left Sun when it got bought by Oracle, doing really cool stuff. They're holding like beers out in the courtyard next door. So if you want to hang out, I'll invite you. Just want to let you know before you take off, and we can do some more questions.
Okay, well, I mean, free beer, we're done. Thank you very much. It was fun. Oh, Kyle, hey, thanks for making this a really cool event. I think a lot of people benefited from this.